Building with textiles is a tradition which goes back thousands of years, from yurts made out of animal skins through to the Roman shade structures installed at the Colosseum. But the inclusion of technical fabrics within mainstream architecture has a more recent history. In the 1960s, German architect Frei Otto pushed the boundaries of membrane technology and opened people's eyes to what can be created with tensile fabric. 20 years later, ArchitenLandrell was founded with the aim of building technically advanced and aesthetically beautiful fabric architecture.
Since I started this company, and it feels like only a few weeks ago, but in fact it's almost 30 years, since those first years, much has changed. Fabric technology has advanced, design and engineering has become computerized, manufacturing techniques have improved vastly. But our original philosophy has remained the same. Few methods of construction can compete with the impression given by lightweight tensile structures. They bring style, curvature, translucency, and clear, large spans to building schemes. We have always thrived on working with architects and designers who feel as passionately as we do about fabric architecture. This presentation is designed to inform, inspire, and get people talking about the possibilities of working with tensile fabric.
The materials of tensile architecture. The materials used to create tensile architecture are constantly in development. As sustainability and performance issues become more and more important, we demand more and more from the technical fabrics we use. The biologically based woven cotton and canvas materials which were used to create the first fabric structures have been replaced by some of the world's most technical man-made fabrics to achieve lasting, permanent fabric architecture. Modern coated fabrics have similar aesthetic properties, but offer significant performance advantages such as increased strength, ease of cleaning, printability, solar shading, and acoustic characteristics. Modern coated fabrics will also resist the absorption of atmospheric moisture, resulting in much longer lifespans and better dimensional stability. In general, we use two generic types of fabrics: structural coated fabrics and mesh fabrics. Structural coated fabrics consist of a woven base cloth made of warp threads that run the length of the roll and fill threads across the width. This base cloth is then covered by a protective layer on both sides. Coated fabrics can be characterized by the fact that the woven or knitted base cloth provides the structural strength of the fabric, and the coating provides weatherproofing, color, and the required technical characteristics such as UV resistance, flame retardancy, and the welding ability. In contrast, mesh fabrics are made up of coated cloth with spacing between the thread bundles. With some meshes, the threads are coated before weaving. Due to the openness factor of meshes, they are primarily used as shading or light diffusing fabrics, but some laminated meshes are available which provide a weatherproof finish with a high level of light transmission. For external use, the coated fabrics most commonly used are PVC-coated polyester, PTFE-coated glass cloth, and silicon-coated glass cloth. They all offer differing properties for strength, durability, translucency, and of course cost. By comparing these with the client's requirements, we can help decide the optimum material for any project. PVC-coated polyester scores well when measured in terms of its strength. It is easy to dismantle and print on, is relatively cost-effective, and requires moderate maintenance. However, it doesn't last as long and has a lower light transmission than other available fabrics. In contrast, PTFE-coated glass cloth offers durability, strength, and Class O flame retardancy. However, it is not suitable for demountable structures and is one of the more expensive fabrics we offer. PTFE-coated glass cloth is often used in harsh climates, such as desert environments, due to its ability to withstand high levels of UV and sand abrasion. For projects where light transmission is important, silicon-coated glass cloth is a viable option. Offering many of the same properties as PTFE-coated glass cloth, silicon has the added advantage of requiring little maintenance and offering high translucency.
Architectural fabrics are going to be changing quite a lot in the future. We're already seeing advances in photovoltaics integrated with fabrics. We're looking forward to better recycling, better cleaning properties, better thermal properties, higher specifications on acoustics, also integration of lighting into tensile fabric.
The forms of tensile architecture. While it is possible to have a flat tensile membrane, the key to strength and stability in tensile architecture lies in the principles of double curvature.
Anticlastic curvature is where the curvature is in different directions or at 90 degrees to each other. When you lock the fabric into an anticlastic curve, as would be seen on traditional shaped tensile structures, you then have a very efficient use of a very thin membrane material that can only carry load in tension. Synclastic is if you have a convex or a concave surface when the curvature in the material is from the same direction.
Tensile membranes can create the most complex dynamic and fluid of shapes. However, the basics lie in 4 geometric forms: the hyperbolic paraboloid or hyper, the conic, the barrel vault, and the inflatable. The hyper is the traditional sail-like form which is often seen as synonymous with tensile architecture. A true hyper is a quadrilateral tensioned at 4 points, too high and too low, to create opposing curves. The theory of the hyper is often applied to other polygonal shapes, and complex undulating forms can be realized with multiple high and low connection points. The conic or umbrella form also adopts double curvature to give it strength. In this case, the loads are spread horizontally around the full fabric form and vertically from the apex to the base. Although featuring double curvature, in much the same way as the previous forms, the barrel vault can only be created with an inner steel, aluminium or timber structure tensioning the membrane in place to create the curves. In the case of all 3 of these shapes, the opposing anticlastic curvature allows the fabric membrane to withstand downward loads caused by wind pressure or snowfall, and the uplift caused by wind suction. At any point on the surface of an anticlastic curved membrane, the 2 different directions of weave are carrying the different types of load. The final form is the inflatable cushion, which adopts a synclastic rather than anticlastic form to create a dimensionally stable shape. Much like a balloon, inflatable cushions are created where constant air pressures form the fabric into a shape. Air pressure maintains the tension under which the fabric needs to be to absorb the environmental loads which will be acting on the membrane, trying to de-stress or collapse the shape. This cushion form is most commonly used with a clear foil material called ETFE foil, but can also be used with more traditional tensile fabrics such as PVC-coated polyester or PTFE-coated glass cloth.